So we talked about what power series are and why they're useful. And it's a good idea to talk about what operations we could do on power series that could help us with dealing with these power series. So we're first going to talk about combining power series, and we have a theorem here. Suppose the power series ckxk, dkxk converges to f and gx respectively on an interval I. That is, f of x is equal to this and g of x is equal to that. Okay. Sum and difference. The power series where we just sum or take the difference of the terms, of we take this term by term addition or term by term difference, convergence to this function f of x and g of x on I. So that's one operation, adding power series together term by term or subtracting them. We could multiply a power series. Suppose m is an integer such that k plus m is strictly greater than 0 for all terms of the power series. Okay? So this needs to be greater than or equal to 0. So you can't choose a k that will make, or you can't choose an m that'll make k plus m negative, basically. If you stay away from those kinds of m, then you have that x times m times the power series is equal to ck x k plus m. So you could basically distribute that xm in. This series converges to xm f of x, okay, for all x not equal to 0. So that's a pretty cool result there. In the way to sort of build a power series from a known function. When x equals 0, the series converges to xm f of x as the limit as x goes to 0. Okay, so whenever you're dealing with the infinite, like we're doing here, taking this power series, sometimes things could get tricky when you're distributing an infinite amount of terms there. So we got to be careful when x equals 0. I mean, it might seem intuitive to just set it equal to 0, but in fact you have to take that limit. Because again, a power series involves an infinite amount of terms. And finally, we have composition. Suppose we have this basic function, h of x is equal to bx raised to the power m, where m is a positive integer and b is a real number. The power series, where instead of x we put h of x, converges to the composite function f h of x, okay, for all x such that h of x is in I. Okay, so again, f of x is equal to this ck xk, and here we're showing that, well, instead of x, we could put a h of x, and we will get f of h of x. And this might seem obvious, but it's far from obvious, because we are dealing with an infinite number of terms. So let's look at where these rules could be useful. Given the geometric series that we see here, okay, find the power series and interval convergence for the following functions. So this right here, well, this is x raised to the power 5 times 1 minus x times 1 over 1 minus x. Well, we're in this number 2 situation here, okay? And so as long as multiplying out this x to the 5th will not cause k plus m to be negative, which here it's not, and this is a 5 here, then this should work, okay? This series does converge to x to the 5th over 1 minus x, and so we can write the power series for this now new function is equal to that, okay? And this geometric series, we didn't change anything significant with the geometric series, so we get the same interval of convergence. What about 1 over 1 minus 2x? Well, this is now the domain of composition, okay? We're going to take h of x is equal to 2x here, and what we could do is, instead of having 1 plus x squared, wherever we see an x, we plug in 2x, and we get now this series for that. Okay, and this is geometric series. So now the ratio is equal to 2x, and that should be strictly less than 1. So x needs to be strictly less than a half for interval of convergence. So you got to be careful with this composition, okay? And notice that the interval of convergence got smaller. What about x squared? Again, we're in composition territory there. Instead of an x, we plug in a negative x squared. Why negative? Because this is 1 minus x, and so if we want 1 plus x squared, we got to substitute negative x squared into x. And so we get this negative x squared everywhere where we had x before in the geometric series with x. And so we'll get these terms here. And this converges provided that x squared is strictly less than 1, which is equivalent to x being strictly less than 1. So that's really nice there, use of the theorem to basically now write the power series for a bunch of functions that we didn't really calculate out and find. We just used a function that we knew the power series for, 1 over 1 minus x, and we used that theorem to get the power series for all of these. Another operation that we could do on power series is differentiate and integrate them. So those are some additional operations. Let's look at the theorem. Suppose the power series converges on this interval there and defines a function f on that interval. Okay, so we're supposing that. We'll later talk about, so far we've been just talking about convergence of the power series, and we'll later talk about whether the power series not only converges, but converges to the function f. Okay, so coming back to the theorem, that power series defines a function. Then f is differentiable for x minus a strictly less than r, and f prime may be found by differentiating the power series f for f term by term. So basically, if f equals this, you could take the derivative of the left-hand side, and that should equal the derivative of the right-hand side. And you could go term by term and take the derivative of this. When you take the derivative of that term there, ck is a constant. The k drops, and you get a k minus 1. The indefinite integral of f is found by integrating the power series for f term by term, where c is an arbitrary constant. So we typically add that arbitrary constant, but we could integrate the left-hand side and the right-hand side. And when we integrate, we get that k plus 1 raised to the power k plus 1. Okay? Again, this assumes we're converging, not only converging, but converging to the function. So let's look at an example of how that's useful. So consider the geometric series that you have over here. Differentiate the series term by term to find the power series for f prime and identify the function it represents. And then integrate this series term by term and identify the function it represents. So we take a derivative of f, which f is equal to 1 minus x, and we get 1 minus x raised to the power minus 2, okay, or that right there. We could also take the derivative term by term of the power series for 1 minus x, and we get these values here, which we could write as a series. Notice that you could write this two ways. You could start with k equals 0 or k equals 1. That's more intuitive there if you would take the derivative of that term. But be careful, because the first term gets killed off by the derivative. Okay, the first term is a 1, and so you do have to adjust your k if you want to represent it in this more intuitive picture of what the derivative should do. All right. Well, then 1 over 1 minus x squared is equal to f prime is equal to that derivative that we just found on the interval of convergence. And we could check the endpoints and the series diverges at x equal to plus or minus 1. You could just plug in 1 there, and it's pretty intuitive that you will get divergence for 1 and minus 1. And so we just found the power series for a new function 1 over 1 minus x squared by taking the derivative of a familiar function represented by a power series. What about integrating? Well, integrating 1 minus x raised to the power minus 1, which is basically the function we're starting with, is equal to negative natural log 1 minus x. Well, that's the integral of the function. Now we could integrate term by term. We get that arbitrary c that we have in the theorem, and we fix that by plugging x equals 0. So if you plug x equals 0 on the left-hand side here, you'll get 1 minus 0. Natural log of 1 is 0. And then on the right-hand side, you also get 0 except for that c, so that means c equals 0. And you get that power series there. And so we just found, by integrating a familiar function, the power series for natural log of 1 minus x. And this also converges for x is strictly less than 1, the same convergence of the function that we started with, but we do have to check the endpoints. Okay, and it turns out that at x equals negative 1, you get convergence by the alternating series test. That's pretty intuitive by just looking at that and plugging in x equals 1, and diverges for x equals 1. So here goes the interval of convergence. Let's continue seeing how the use of integrating power series is useful. So find the power series representation centered at 0 for the following functions and give their interval of convergence. So here you have arctan x, and you think, well, how am I going to find that? Well, we found before the expansion for 1 over 1 plus x squared. So there you just take the series, the power series for 1 over 1 minus x, and you just put x squared, negative x squared, wherever you see an x. And so you get that series, that power series. And we know arctan is the integral of that. And so we could integrate term by term, and we end up with this term here. We got to fix c, so we use 0 is equal to arctan of 0 is equal to plugging in 0 for all of these. Okay, we just get that plus c term, and so that means c is 0. And so we just found, using integration, clever integration, the power series for arctan. And we do have the same interval of convergence with what we started with, which is x is strictly less than 1. We got to check the endpoints. And it's pretty straightforward to check the endpoints. Both 1 and negative 1 are alternating series. And so it's clear that by the alternating series test that this converges also at the endpoints, and so you get that interval of convergence. What about natural log of 1 plus x over 1 minus x? Well, here we just found what the natural log expansion is over here. And we could substitute instead of instead of x, we could put minus x to get the plus, and we plug that in the equation. We could write out the terms, and we get that power series there. Over here as a side, so not part of the problem, we're done basically. Sometimes you'd want to do this like by adding the terms together, and I make a note here of how you can take out that sum and add the terms together. You'll end up with something like this. And over here I end up reindexing just to get a nice sort of form. And this equals 2 or 0. It's 0 when k is even and 2 when k is odd. And so we could sum, instead of over k, we could sum over 2n plus 1. Okay, just that, what that does is allow you to just skip the even ones. Okay, and so that's why we these two ways agree at the end if you decided to just manipulate the arbitrary terms in the power series.